Hey guys, so what we're going to do is we're going to talk a little bit more about just trying to wrap up that wave terminology. All right. Now, a couple of things that I want you to think about. First, remember that the point of a wave is to transfer energy. And what we're seeing here is that the compressions are moving to the right. And so they're transferring energy. Even though the particles themselves are just kind of moving back and forth, there is energy being transferred to the right here as time progresses. All right. Now, I want you to try something for me. I want you to put your hand in front of your face, just like this. You're not too cool. You can do this. All right. Hand in front of your face. Move it back and forth about 50 centimeters with a period of about a second. Now, remember, period is the amount of time it takes to complete a cycle. So 1 1000, 2 1000, 3 1000, 4 1000, right? Every second I'm completing one period. Okay? Now what I want you to do is I want you to double the frequency. So doubling the frequency means that I need to complete 2 cycles per second instead of 1 cycle per second. So I'm going to go 1 1000, 2 1000, 3 1000, 4 1000. So I'm going twice. Essentially, my hand has to go back and forth twice as fast now. Same 50 centimeters as before, still going back and forth, but now my frequency is double. Now, I hope what you're recognizing is that that takes a lot more energy, right? You transfer more energy by increasing your frequency. So higher frequency means higher energy. Now, it doesn't actually mean that your wave is going to go faster. It just means that the wave is able to transfer more energy because the particles are going back and forth more often. Now, try this again. Go back to your 1 1000, 2 1000, 3 1000, 4 1000, all right? Just going back and forth about 50 centimeters. Now I want you to double your amplitude. So still 1 1000, 2 1000, 3 1000, 4. So, right, you're still going back and forth, right? 1 second. The period's the same, meaning the frequency's the same, but now I've got a larger amplitude. Hopefully, again, you're recognizing that that takes a little bit more energy, right? So increasing the amplitude also increases the amount of energy that we can take. Okay, so this is going to be a big idea over the next couple of days of classes, recognizing that higher frequency means more energy being transported and higher amplitude. And again, the particles may move faster, but the wave itself doesn't necessarily move faster because we're putting more energy into it. And I'll show you that in a couple of different situations here in a later video. Okay? So let's go ahead. We're going to move on to the next little bit of this discussion. So in the next couple of minutes, we're going to talk about how each of these things applies to different types of waves, right? We talked about period, we talked about frequency, we talked about amplitude, and we talked about wavelength. How do we get those, and what does it mean for a longitudinal wave and then for a transverse wave? All right? So let's go ahead. Period. Period is the amount of time it takes to complete a full cycle. Now, with longitudinal waves, we see that this is what the cycle is. We have a compression, and then we have a rarefaction. Then we have a compression, then we have a rarefaction. Then compression, then right. You can hear that it's cycling through a compression, rarefaction, compression. So one cycle is from going from one compression to the next compression. And so I need to find out how much time it takes. Now, you may also be astute enough to notice that there's a bar over here at the end, which is actually causing that wave. It's causing the disturbance, right? That vibration going back and forth. Now, if you see that, you could also just measure the amount of time it takes it to go to the right and left. And you can get the period from that. How long does it take it to complete one full cycle? All right? So either way, however you want to do it, I'm going to go ahead and just draw a line on here, right down the middle. This is just a random position. And then what I do is I use my fancy Sanchi stopwatch, and I wait till I see the compression get there, and I go start, and then stop. And so I started and stopped on a compression. So I measured the amount of time that it took to go from one compression to the next one. Now, experimentally, it would be better to measure maybe 5 of them all at the same time, and then divide by 5 to find out the length of one of them. No matter what, you should probably get something around 2.4. Okay, so we're going to say that the period is about 2.4 seconds. Okay, it's an amount of time. It takes 2.4 seconds to go from the beginning of one compression to the beginning of the next compression. All right. Now, frequency, we're not going to have to measure. If it were happening fast enough that we could count how many happened in a certain amount of time, then we could do that. But in this situation, it's probably just going to be easier to measure the frequency through calculation. Remember that the period is equal to 1 over the frequency, or the frequency is equal to 1 over the period. And so we can actually just calculate the frequency. So the frequency, we're going to go frequency equals 1 over period. And so that'll be 1 over 2.4. And so then this one we are going to punch into our calculator here. We're going to go 1 divided by 2.4, and I get 0.42. Now for the units, you can either write cycles per second, or you could do 1 over second. In math class, you may have learned that sometimes it's okay if you have radians, that you don't actually have to write the word radians. You can just write down the angle without having to write that word. Same thing with cycles. We already understand that if we're talking about frequency, we're talking about the number of cycles. Kind of like for the period, we didn't have to say 2.4 seconds per cycle because we already know we're talking about one cycle. So you don't have to put that. You can do 1 over s, or more commonly, you'll see it written as Hz, hertz. How many hertz? That's the frequency. And that is SI. That's 1 over s. That's from our fundamental units. And so we can use that unit as well. All right. Next up is amplitude. Now, amplitude is the maximum displacement from its center. Okay, so what you'll need to do here is you'll need to pick one particular particle. Okay, so I'm going to choose this one right here. And it looks like he goes from about right there to about right there. So you can see he's going back and forth between, I tried to label the middle as best I could of those. And so that's where that particle is going. Now the middle of that particle would go straight down the middle. The middle of its oscillation there goes from one to the other. This would be the middle. Now the question is, what is the maximum displacement from the center? Now the easiest way to do this probably is just to measure the distance from one point to the other. So I measure that and I get about 2.6 centimeters. And if I have 2.6 centimeters, that means the middle has to be at half of that, 1.3. And so therefore, we could say that our amplitude is about 1.3 centimeters. Now, if I want to put it in SI units, then it would be 0.013 meters. But it's also okay to put it in terms of centimeters or millimeters or whatever else you need to, as long as it's a length that corresponds to amplitude there. Okay? Now the last one is wavelength. Now wavelength is the length of one cycle. Now remember when we did the cycles before, we went from one compression to the next. So the length of one cycle is how far is it from one compression to the next one. Now that's actually pretty difficult to measure when it's moving along. You might be able to do it, like if I kind of watch this one and just kind of see when it passes through, right about there. Maybe compression on both of those. You can kind of see that, right? And so you could measure that as being the wavelength from one compression to the other. It may also be easier. I've actually frozen it. I took a screenshot here. And so it'll be a little bit easier to measure from one compression right here. That's about the center of one compression to the center of the next compression right there. Like that right there. And so I can measure, this is one compression, that's the next one, so that would be the length of one cycle, the physical length, not the time length, the physical length. Okay, so I can measure that, and here I got about 9 centimeters. Okay, so we would say the wavelength is 9 centimeters. Or again, I could do 0.09 meters or whatever if I needed in SI units. Okay, if you're doing calculations with it, please put it in SI first. If you're just writing it down, then it's okay to use whatever other units you have here. Okay. Now, obviously, a better way to do this would be to measure several of them, right? So I could put another line here, another one here, another one here, right? And I could go down maybe 5 or 6 different wavelengths. Okay, so there's one wavelength, there's another one, there's another one, right? And I could measure several of them And so I've got 1, 2, 3, 4, 5 wavelengths there, and I can measure this whole distance from there to there, which would be about 43.3, and then I'll divide that by 5. And if I do 43.3 divided by 5, I get 8.66, which is going to give me a slightly better answer, probably a little more precise, right? Because I'm not going to have as much uncertainty on the ends. That uncertainty is going to kind of even out a little bit. So, you know, however you do it, that's fine. Just recognize that the wavelength is the distance from one compression to the next. There are better ways to do it mathematically, and there are ways that we can just do it if we want a rough estimate. Okay? So that is all of those things for a longitudinal wave. What I want to look at now is a transverse wave. All right? So let's have a look at that. All right, so we're going to do the same thing now for a transverse wave, right? We're finding the frequency, the period, the amplitude, and the wavelength, just so that we can interpret these in a different situation. Now, with the longitudinal, we had compressions and rarefactions. With transverse waves, we have what we call a crest, that's the top of the wave, and a trough, which is the lowest part of the wave. And so you can see that the particles here go up and down and up and down and up and down. So the top is the crest, and the bottom is what we call the trough. Okay, so crest, trough. Crest being the top, trough being the bottom. Like what you would see with a water wave when you go to the coast, to the ocean, to the beach. Right? So let's see if we can find the period, frequency, amplitude, and wavelength. So for the period, remember with the last one, we found how long it took one compression to then pass to the next compression. All right, so we're going to go ahead and just kind of draw a line here. Okay, and when we draw this line, we're going to start our stopwatch at the moment that the crest passes this point right here. And then I'm going to stop my stopwatch when the next crest gets there. Okay, and we can get better data if we measure several of them. And so that's actually what I'm going to do, is I'm going to actually measure a couple of those wavelengths right there. So stopwatch, here we go. So I'm going to count maybe 5 waves. Okay, ready, set, go. 1, 2, 3, 4, 5. So I'm going to count 5 waves from this point, right? Ready, set, go. 1, 2, 3, 4, 5. All right, so I got 4.84 seconds. So I got 4.84 seconds for 5 waves to pass by, 5 complete cycles of this process, right? You could also watch an individual particle and just see how long it takes. The period's the same, right? The amount of time it takes that period to go up and down should be the same as the period, the amount of time it takes the wave to go from one crest to the other. Okay, so we've got 4.84, so I'm going to take that 4.84 and I'm going to divide by 5, and I got a period of 0.97 seconds. Okay, now we'll move on to frequency. Remember, we can get frequency really easily because frequency is just 1 over the period. So I'm going to go 1 divided by that number, right? That's this right here. Frequency equals 1 over the period, and I get 1.03 hertz. Now that should make sense. The other one was going pretty slow. This one, dun, dun, crest, 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 crest. Those are happening much more rapidly than the compressions were happening in that longitudinal wave. So our frequency is much higher. It's a much more large number, whereas the period is a smaller number. It takes less time from one crest to the other. We can do the amplitude. Remember, amplitude looks at one particular object. Now, if you wanted, you could find the center of kind of this crest trough here, and you could measure how high it went and how low it went from there. What's the maximum displacement from its center? It's easier in a situation like this to just look at one particle. So I'm going to look at this guy right here. It looks like he goes all the way up to the top, and then he goes all the way down to the bottom right there. So that guy right there is going up and down. All right, so I'm going to measure that distance right there. And I get 7 centimeters, 7.0 centimeters. But remember, I need to find the maximum displacement from the center, so it's going to be half of that. Okay, from the center it goes up there, back there, down to the bottom, back there, right? So for those that know sine waves, it is a sinusoidal wave, and so my amplitude here is going to be 3.5 centimeters. Okay. From there, we can now find the wavelength, which is the length of one cycle of a wave. Okay, and so in order to do that, again, remember in the last one I paused it, so let's pause. And here we go. So it's paused. We can now measure from the top of one crest to the top of the next crest. You could do from the bottom of a trough to the bottom of the next trough. You could measure a couple of crests and divide it. Any of those things are fine. We just want to know the distance, the length of one of those waves, so from one crest up to the next one. And I've got about 50, if I put this in the middle, I've got about 56.8. So my wavelength there is 56.8 centimeters. All right? Cool. Now, I want to show you one last thing before we move on to kind of the next segment of this. This is kind of a neat thing. The wavelength is how long the wave is, right? And that's a length. The frequency is 1/seconds. It's how many waves go through in a particular amount of time. But what happens with the units? What happens when I multiply centimeters times hertz, which remember hertz was 1/seconds. And if you want to be literal with it, the frequency was cycles per second. And the wavelength is the length for one cycle. So the cycles cancel out and we're left with centimeters per second. All right? Now what this means is we're going to get one more formula here, which is that if I take the wavelength and multiply by the frequency, the result is the speed. That will give me the speed of the wave. How fast is it moving? And we'll look at this a little bit more in our next series of videos, but recognize that if I were to take the wavelength and multiply by the frequency, it would give me the speed of the wave. This is going to be one of the most important equations that we use in this unit. All right? And that's it for now. I'll see you next time.